Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Computer Lab, John Crowcroft. Of course, to everyone from Cambridge, he's very well known. He was on our technical advisory board for a few years, regular guest at Microsoft Research, especially when we were still in the old building, right next door to the Computer Lab. But he's come here today especially to talk about the once and future internet. Over to you. Thank you, John.
Okay. Hello, everyone. The after lunch slot is always a terrible one to have, so I'll show you how not to do an excellent research talk, and then Simon can correct that afterwards. That's like my goal is to give you two lessons, one of which you'll forget because I'll do it badly, and then the other you'll remember because Simon will show you what I did badly. So this is me. If anything strikes you as interesting that I say and you want to follow up afterwards, do email me. I'm a professor in a computer lab, which is about a 15-minute bike ride from here, so it's an immense distance. It's in the sort of wasty, snowy, far northwest of Cambridge, miles from the railway station, literally two. So I wended my way here rapidly to give this talk, and I'm very happy to have been asked along. So if you're wondering what this thing on my wrist is, this is relevant. I spent 6 days in a field in southwest of England at the Glastonbury Festival with a large number of unruly children. They were the people on the stage, actually. I had my family with me. They're quite well behaved. Why is Glastonbury relevant? Well, Glastonbury Tor, of course, was partly connected with all the legends of King Arthur. And, of course, King Arthur is supposed to be somewhere in the Isle of Avalon, which is sort of that part of England. It possibly is the Isle of Avalon. And so one of the themes of my talk is the future of the Internet going to be Avalon, which is a sort of place of beauty, a sort of Arcadia or an Elysian field somewhere, or is it possibly going to be the other dystopic vision that T.S. Eliot had, which was at the end of the story of King Arthur, there's this horrible wasteland. And I know most of you are computer scientists or even life scientists. You may not have read that poem. It's quite long, but I recommend it to you. It's quite worth reading if you're into that kind of thing. And the Once and Future Internet is also sort of stolen from another bit of Arthurian stuff. There was a very nice kids' book, which was a sort of simplification of the legend of King Arthur, written by T.H. White. It's a beautifully written book, and there's an adult version of it, a grown-up version of it, called The Once and Future King. And it is about the sort of the promises of this wonderful thing that was the Knights of the Round Table, almost democracy, except they were knights and they were serfs out there. Anyway, let's not dwell on the problems of early medieval society and legends, but that's where the title comes from. And if you haven't read The Once and Future King, I recommend that to you as well. Or you could read the Mort Arthur or many other things. But that's where the abstract and title came from. So, can I kill anyone with this laser? No, I won't. It's okay. Okay, so the internet is quite old. I started working on stuff to do with the internet. I was a graduate student at University College London, where I noticed some of the poster speakers come from. I was in the computer science department there in 1980. And somebody came along and said to me, would you be interested in connecting stuff up? We're thinking of connecting all these computers, and we've got this box we want to connect to America over a satellite, and that was the first router outside America that was on the internet, together with some other ones in Germany and Italy and Norway. Bizarre choices. And actually, we also had a link to Cambridge over another satellite link, connecting a bunch of local area networks together using a thing called a Cambridge ring, which was much better than the Ethernet, but never went anywhere, sadly. And we ran these protocols, which were the communication stuff of the internet. Before 1980, you may hear people tell you the internet's been going since 1973. They're wrong. Even if their name is Vint Cerf, they're still wrong, because it wasn't the internet. It ran a bunch of protocols called Network Control Protocol, Network Control Program, and it was in 1980 that we switched over to these new protocols, the Internet Protocol. And what was different about the Internet Protocol is it connected lots of networks together. So it was a network of networks. So this was a big switch because we had all these single kinds of network, and suddenly we had this way of connecting networks and networks. And from the get-go, from day one in 1980, we had a satellite network, So the US, large geostationary satellite connecting Western Europe and eastern seaboard of the US. We had packet radio networks that were jeeps driving around with radios, and we had the ARPANET. So we had at least 3 networks. Actually, there was a MILNet, which was a dark secret network, which I don't know anything about, and I'll have to take you out and shoot you if I told you anything by mistake. And there are a number of design principles that were behind all of this, which are actually pretty subtle. And actually, in several areas in computer science, these kinds of principles reappear that you know, we're familiar with. But back then, it was actually quite a surprising thing to have got these principles embedded in this design. So architectural principles, we hear about computer architectures, processor architectures, and a set of sort of design principles like RISC. We hear about software architectures, and they've got a communications architecture, and it incorporates things that are common with software engineering, like modularity and abstraction and so on, a layered system, operating systems, layered systems and modular systems, and the layers abstract the detail below and so on. The standard stuff that we're used to now. But back then it was quite visionary of people to think of this, particularly since a lot of the early internet community were kind of engineering folks and they didn't know anything about software really, and they were writing all this software and they had to engage with a bunch of us horrible computer scientists in UCL in London and Cambridge and England and MIT and Harvard and various other places that were building this stuff. We started writing the software and building these protocols and so on. And there are a number of things that are abstracted in here that abstracted away detail of how addressing works, how routing works, how reliability and robustness work. And the layering allows you to hide all of that, and then at the top of all these layers you have applications and users. So that's just sort of standard stuff. In the early days, this was not an easy-to-use system, and one of the reasons I got a job doing this was actually very few people here know what I'm talking about, but I actually knew how to use a system called TOPS 10, which is a really obscure old operating system, and that was one of the computers we were using, ran this DEC operating system, and I knew how to use that as well as Unix, and so I could actually use both kinds of computer on the net from the get-go. It wasn't easy to use, it was obscure. Ease of use came along later, so even at the very level everyone's been used to for the last 20 years of having nice names for stuff on the net, service names or URLs for websites, we didn't have that. We just had numbers you had to remember. So we all went around remembering things like 10.0.0.1, which was the file transfer protocol server at the Information Science Institute in University of Southern California. Or I would remember numbers like 14.0.2.3, which was my router's address. You know. So, and when I rebooted all the routers on the satellite network and hoped that they would come back, if they actually, the new software actually didn't crash immediately, I knew what all the addresses to ping were. So I go around with these things etched on my heart, practically, as you do. It's a bit like debugging the output of bad C compilers. There are a number of other principles that were embedded in here. One of the interesting principles in the internet we'll get onto is resource pooling. And people here, Peter Key notably in this lab, has done work in resource pooling. It's a very interesting idea. It's the idea that was not present in other networks. The idea of other networks was a bit like, at that time, in the 1980s, was that if you set aside resources for some users, even if they don't use them, other users can't use them. So it's sort of kind of selfish network. That's actually a really dumb idea. So it turns out that users as humans or users as programs are very bursty. They have statistical properties, and that you can take advantage of those properties in lots of nice ways. And an awful lot of work has been done by people, I guess notably Leonard Kleinrock is just past 80 years old at UCLA, worked on all the fancy maths for that, but it's still ongoing. It's still very interesting in that area. But there's some crucial design principles I want to get into some more detail about, because you'll see where I'm heading when I get on to talk about the future internet. And one of the crucial design principles is the network's decentralized. Decentralized, no single point of failure. Okay? So where are there centralized systems? Well, if you've ever gone through an airport and the air traffic controllers go on strike, then you don't go anywhere because there's a single point of failure, the air traffic control. Right? So that's not a good plan. And in fact, the early design principle of the internet was to be survivable of accidents or deliberate attacks that envisaged a critical infrastructure that everyone would depend on, so it better work even if some bits of it's blown up by asteroids or tsunamis or bad people. So decentralization was crucial. I've already mentioned statistical multiplexing. This is this nice property that you get, that you can share resources, and if somebody just doesn't happen to use all the resources they thought they were going to use, other people get to go faster. The simplest illustration of this is the fact that when you download a video or you view a video, the progress bar is ahead of where you're watching usually. Not always, occasionally it stalls, but it's usually ahead of where you're watching, and that sort of says that was a good design choice. That's a good thing to do if that usually happens. It depends on the total resource and total demand, and sometimes it doesn't work. Gosh, that's a bit like road systems where everyone decides to go in their car today because it's raining, and it takes you an hour to get from the computer lab to the railway station instead of the 10 minutes it would take by car on a nice weather day, or the 15 minutes it takes either way on a bicycle. Another design principle is this end-to-end principle. This is actually part of layering. It's not a particularly new principle. It was a systems mantra that people at MIT came up with, a group of people that worked on operating systems and on communication systems. And the end-to-end principle was just simply the idea that if you're going to layer things, don't put any functionality in a lower layer that isn't used by everyone above. So each layer is you keep it simple, if you like, only as simple as necessary and no more. And that led to the idea that the internet protocol layer is incredibly simple, mind-bogglingly stupid. And people go, we had fights with people about this, almost physically. People all the way through the 80s from other kinds of network, they would look at us and go, that can't possibly work. People would tell me, you'll never be able to do video over the internet. You'll never be able to do audio over the internet. And I'd be chatting to somebody at MIT over the internet using video and audio in 1988. And I'd be showing these people, they say, no, that can't work. So, because this was too simple to work. And they're wrong. We were right. It does depend on some resource pooling working and understanding statistics of the traffic, which is very important. So end-to-end design mantra is very important. That should say Swiss Army knife. Don't put a kitchen sink or a Swiss Army knife in the lower layer of your system. Keep everything very, very simple. In operating system terms, if anyone does that, I didn't notice too many posters from that kind of background, but that would be sort of microkernel view of the world, if you like. Or if you're into cloud and virtualization, that would be a simple hypervisor, probably not the Zen hypervisor that we wrote, which is massive and daft. And then there's another interesting principle named after one of the important early guys in the internet community. John Postel came up with the Postel principle, which is basically it's an implementation guideline, but it's also a protocol design guideline, which is if you design a protocol that's got lots of bells and whistles, be careful to handle any of the bells and whistles that get used by the other person, but don't use them yourself. Right? So he phrased it as be liberal in what you accept and conservative in what you send. And I have no idea why PowerPoint did not correct my spelling. Teach me to use a Mac. Postel was a very nice guy, a bit of a sort of left coast hippie libertarian, if you ask me, but nothing wrong with that. So we had all this stuff and it kind of worked, but it wasn't very usable. And for about, I guess, 12 years until 1992, we were all using this thing, but we were all kind of, I used to talk to people at dinner parties, as you do in London or Cambridge, and mention the internet was coming, it was going to be very important. They'd all look at me like you're a complete mad person. What drugs are you taking? And I didn't, I just had the coffee. But then a nice Englishman, Tim Berners-Lee, came along. He actually spent about 4 years going around everywhere talking to people saying, here's this thing we could do. We could share lots of content between people in this really nice way by making it available through naming objects in a way that tells you what protocol you need to get at the object, where the server is that object lives, and where on that server it is, what's its file name effectively. So he came up with hyperlinks. And actually in 1988, I remember him going around various universities in the UK. He was based in CERN in Switzerland. But he went around places saying, here's this thing I've done. And how would you do the protocol, which actually turned out to be HTTP? How would you do that protocol? And we suggested various clever things, and he ignored us. We were wrong, and he was right. He did a very simple protocol. And he also did a very simple markup language, which allowed you to create pages with links. That's all the really important thing in there was. What's really important, though, was he completely blew away all the people working in distributed hypermedia at the time. So if you're into distributed databases, there were distributed hypermedia databases that people have been working on for 30 years at this point. We're talking in 1988 to 92. There's 30 years of track record on hypermedia distributed data. So that's lots of objects linked to each other. And you know what he said is, you know, in the internet, you never really know what the other person's going to do. So if I link to them and they change things, well, I'll have to figure it out later. Whereas the hypermedia people said links should be bidirectional. So if you put a link to somebody's site, they must have a link back to you. That doesn't scale. You can't add stuff unilaterally. You have to agree with everyone. So as you add more people to the internet and you scale the internet, at this point, website growth from 92 went from nothing to 1,000 servers in less than a year, and then it just kept going exponential, so it was doubling every year. So can you imagine if every time you had a server, you have to contact 1,000 people, and then 10 years later, 1 million people, and so on. This doesn't work. So he was right, and everyone else was wrong. Very, very simple. Extremely simple. So the internet is very simple, or is it? So from about 92, we had sort of up until this point had a sort of very easy time of things. We hadn't had any bad stuff happen, despite the fact that there were sorts of military networks connected, but most of it was nice, friendly, fuzzy research labs in universities and a few companies that were involved. But nothing particularly bad happened. About 92, there's a sort of crucial turning point in various technical ways, but also socially. The number of people grew to the point where there was probably some mileage in trying to attack the network. There might be somebody out there with some information you could steal that might be worth money, or something you could attack and get a reputation for being a cool hacker. And those are kind of two classic motivations for bad people. There are lots of studies in the last few years which actually go and interview people about, why did you do this bad thing? One of the very early worms that attacked the internet around then was an MIT professor, who's still an MIT professor, and he did it because he could. He didn't think what would happen if you hit go. Truth in advertising, I got interviewed by a newspaper in England about that, about a week after that happened, and I wrote a worm to show the newspaper journalist how it worked, and I hit go and shut down UCL's network. And I got banned as an academic from using computers for a month. Mea culpa. And, it was easy to do. You think, hey, it's cool, I'll do it. And, that's not a good idea when the thing's going commercial. So 92 is a crucial point in the history of the internet, because that point, all these subsidized networks coming from government agencies like the military and the universities, they stopped their money and they said, you better go buy this from a commercial organization. So they created commercial internet service providers. At the same time, they created some other cool things, which I'll get onto in a second, but one of them was a decentralized way of managing interconnect between commercial providers. How do you deal with the fact they have different commercial relationships? They're not all necessarily friendly and fuzzy friendly relationship to each other with the same motives. They have their own customers and their own business goals. So that had to be embedded in the interconnection rules somehow. We'll get on to. So there's a whole list of bad stuff has started happening. Worms, the first thing, viruses, malware, been around forever, but now sort of big time. Distributed denial of service attacks is an interesting one, because the internet had this very naive model of what traffic looked like, as I've already mentioned. So if you could take over a number of computers and use them to send traffic to one site, you could deny service by using up all the capacity for that site, and that still is a bit of a problem. So we see things like botnets, exploited machines, vulnerabilities in software exploited. There are ways to fix that, perhaps. We've done work with Microsoft here and some cool stuff. And of course, there are other things which deny service at another level. Cambridge University's email service actually has 98% of mail arriving at it classified as spam. Right? So we're actually running multiple megabits a second, 24 hours a day for year on year. If you work it out in sort of kilojoules burned, it's pretty bad. And actually the system for filtering is awesome. Almost everything I get is legitimate email, but there's this amazing amount of other stuff that's just out there. It's a bit like sort of the junk DNA or the sort of noise in your system, the biome that's not the useful bits of it or whatever. Okay, so these were the bad things started happening. Bad things went on happening. There were lots of bad things went on happening. This is very annoying. Piracy, of course, was one of them. Now we've moved on to more legitimate models of you upload your video to some company server, like let's say YouTube, and then rather than asking permission, they ask forgiveness. They go to the copyright owner and they say, is it okay for us to have this content here? We'll give you some advertising revenue. That's the sort of Jesuit solution, right? You don't ask permission because it wouldn't scale. You ask permission for every item uploaded, it would take too long. You just let people all around the world do your job for you, uploading lots of copyrighted content and deal with the thing after the event. That's pretty clever. So the YouTube model and other models have come along where advertising revenue makes people happy, or even just analytics makes you happy. Why does this work, though? This works because people forgot a design goal of the internet, which was decentralization. The cloud, we're responsible for in Cambridge University, with some people from Microsoft. We did one of the first cloud implementations, Amazon's EC2 service. We wrote the software in the university. Paul Barham, who's at Microsoft in Silicon Valley, was one of the guys who helped make sure the Windows operating system worked on our hypervisor. But we did the Linux one, which he couldn't look at because bad things would happen if he saw GPL code. But that's another story. So we managed to do that. That was very cool. And along came other people that did cloud businesses too. But it's basically you put all your eggs in one basket. You put all your boxes in one big data center, and then what does that buy you? It buys you several things like manageability and scalability, lots of ilities. But it also buys you a business model, which is now you've captured all these customers, and some of them are meta customers. They're people that run a service. They then have customers, and you've captured all the data about those customers. So what can you do? Well, you've now got all this data. You can run analytics on it. Analytics is AKA market research, right? We can do lots of very clever statistics. We can do machine learning and infer what people are going to do. Is that all good? Well, perhaps it is, because it means that people get a service for free. They don't pay money for it. But then, of course, what you use these analytics for is deriving how to charge people to advertise and then targeting ads at people. It's not free. You put up with eyeball time or your attention span. You actually have to look at this stuff. So this is not necessarily a good thing. And in fact, the bottom line here is, the bottom line on this slide is, this got weaponized by security services. They went off and did a backdoor exploit on it by using secret courts in America to require centralized cloud providers to give them access to all this data, all these services, all your stuff, right? And that's not necessarily a good thing. That means there are weaknesses in the security of the architecture, the storage, the processing, the transmission. Those weaknesses, you might trust the NSA, you might not. You might trust GCHQ, which is the British equivalent, or Five Eyes, the 5 countries that all agree to share this stuff. On the other hand, if they have access, there could be some bad person there. How many bad things do you think happen a day by somebody in one of those agencies who's not acting under orders, they just decide to do something bad? Lots, right? Lots a day. Same thing happens with police databases, but they don't put those in the cloud. Okay, so what's going to happen next? I was going to talk about the future of all this stuff. Where are we going to go? Well, I'm going to say some things about we should, and then I'm going to say things that will happen, and then I'm going to go back to what we should do more carefully. So we ought to recover the original design principles and figure out how to do a decentralized cloud. And I'm going to give you some hints about how that might happen. It's not easy. It's not that hard if you keep the principles together. So you do the same thing for cloud services, applications you might use, whether it's Flickr or Facebook or Bing Translate, or doesn't care. You could do those in a decentralized way. Another interesting thing to tackle is incentives to reduce certain kinds of abuse. That might involve accountability for behavior. That can be done in a decentralized way. And maybe we could then reduce or remove analytics or advertising as the business model. Maybe you could go back to a business model where people pay, or maybe it's free. You just pay for your bits to be moved around and nothing else. And I'm not the only person who thinks that might be a viable future. One of the guys who used to be here is now at UCL, I keep mentioning, George Denizis, a security researcher. He's strongly of the position, as am I, that actually a very tiny amount of money additional to your current payment for an internet service, whether it's on a smartphone or on a fixed line, would get rid of all that advertising and therefore get rid of the analytics and therefore get rid of the privacy problem. And that's just a switching incentives. There's a lot of work going on here in that area, which is interesting. It's a bunch of game theory and economics meets computing and system design. If you're interested in mechanism design, it's very cool. So could we go back to that? Now, the second thing is a very interesting area, which I think is much more ambitious. So my first one is ambitious enough. The second thing is really ambitious and crazy, which is one of the original goals of having the internet at all was to support distributed intelligence, not NSA-style intelligence, but people-style intelligence, decision-making by groups of people. When you get a group of people together to try and decide something, it seems, anecdotally, that they are less intelligent than the most stupid person in the room. When you try and do distributed intelligence making and decision making, it seems that things don't happen well. Very occasionally, everything lines up and you get some amazing, something works. We haven't figured out how to make that happen systematically And we really haven't figured out how to make it happen online systematically. So actually building applications that support distributed intelligent behavior by sets of people would be a good thing. But I think that's a mind-bogglingly difficult problem. And I'm not talking about AIs. I'm talking about just support for people that deals with the fact that once you go online, all kinds of people start to misbehave. And as the group size goes up, the misbehavior grows faster than the useful communication. So how do we deal with that? And I don't have an answer. So that would be a future goal I would like to see. We have built all this fantastic infrastructure. We can improve the infrastructure, make it more privacy preserving. But it would be very cool if we could also actually support cool stuff where there's a problem in the world, there's a tsunami, there's an earthquake, a bunch of people who still have communication facilities want to do distributed decision making to figure out whether they send physical resources to solve that problem. How do you do that in a good way? And we have old-fashioned organizations for that. Emergency first responder things have a bunch of techniques. They don't always work, so it's a fun area. Okay, some less ambitious things I'll just briefly mention, but these are just going to happen. But they also cause us some cause for concern. And one is Internet of Things. I have a thing here. That's one kind of thing. But there are lots of kind of things in your life. Home environmental control, heating, lighting, air conditioning, whatever. Finding out if the fridge light really goes off when you shut the door. That's a really important Internet of Things service, I think. I've always wanted to have a webcam inside the fridge. So when I'm in the shop, I can look at what I haven't got in the fridge and decide what to get, right? So, or even look at the sell-by dates, the best-by dates, that would be cool. Home entertainment, obviously we have everything internet, so there's 6 people in my household. I think every single sound and video system is IP-based. There's no old analog magic stuff anywhere, except when it goes to your ears and eyes. The entertainment systems, utilities, power, and so on. This is just going to happen. So Internet of Things, including the larger scale Internet of Things, which is smart cities, where we instrument all of the transportation systems and the power grid for the city, and maybe security and so on. These are all good things because they just optimize stuff we do. And it's like obvious and it's easy. Actually, of course, there are some downsides here. A lot of the gadgets people put into houses and into sensors in buildings have no security, so this is going to go horribly, horribly wrong. My favorite example is the braking systems that was sold by one company to multiple car vendors in the US, which had Wi-Fi, so you could do diagnostics on the brakes, and then somebody at University of Washington, Seattle demonstrated turning the brakes on and off remotely with no access control. Really bad. But there are many other examples. One was a colleague of mine was scanning a bunch of building HVAC systems, monitoring what they did, and he found hospitals where if you sent a malformed packet by mistake, you crashed the hospital heating and lighting system because they had no access control, no password, no firewall, anything on this box. And it was embedded system software written by somebody who hadn't learned programming or used bad programming languages. Maybe they used C11 with the residual mistakes we saw outside in one of the posters, but they probably didn't get anywhere near that kind of level of sophistication. So, and as we move up the stack, other things you're going to see, future Internet of Stuff that is going to include, obviously, mobile e-health, monitoring your health. That's just going to happen. It's really, really good. The starting point would be well-being, and we already have devices that measure your well-being and report it back to your web service, and then you can, then you don't have to worry quite so much about attacks on your well-being. But then we start to put insulin pumps onto the internet so we can actually adjust things based on the latest scientific results and download that to people and upload readings from them and so on. All this is good, provided we deal with security. And of course, other things where the network will vanish into the environment and we'll all deal with it with gestures and all the kinds of cool stuff that happens with user HCI stuff here and other places is just going to be, that's how the world will work. I won't have to hold this object. I'll just be able to go wave at something in the right way. And so on. Those are all good, but they motivate fixing that centralized problem, the privacy problem, the security problems of that centralized system, because they're all much, much more dangerous things could happen with this than just leaking lots of information, right? I mean, really bad things can happen if you can turn all the lights green in a city. Anyone remember the Italian Job? Not the remake, the original one. Or turn them all red. I mean, that would be more fun. Actually, there's a story about that. There was a mayor, I think, in Liverpool whose daughter was getting married. And he borrowed the remote control for the traffic lights from the ambulance service so they could drive through a green wave of lights. So we already have systems that do that, and they can be misused. That's a misuse. Not dangerous, but that could have led to danger if there were 2 mayors and they both set the lights green, right? So we can easily imagine lots of bad things. So we need to fix this. So let's deep dive for a few minutes into this decentralization idea. Okay, so, and I'll take questions at the end. Sorry, I should have said, there's an example for Simon PJ after this talk to go, no, Crowcroft, you should have engaged with somebody and got their name and said, okay, have you got me so far? Are you with me? Right, he'll do that better. Okay, so one of the underlying ideas of this decentralization actually comes from biology, biological systems, and ecosystems. It's called highly optimized tolerant systems. Very, very cool work. I'm looking at entire ecosystems and evolution. A guy called John Doyle at Caltech did a bunch of work on this, and you can model the decentralized nature of the internet before the cloud in a very similar way. This has a nice property that failures are localized. You can't actually, with a non-centralized system, it's very hard to have a single point of failure crash everything. There is an exception. You could have emergent behaviors in a decentralized system where things synchronize by bad luck. This actually happens in some badly designed protocols, and every now and then we have to go fix them by deliberately putting in randomness, which my favorite bit of computer science is putting randomness into things. So, we want non-determinacy. We don't want synchronization. We really, really don't, in some cases. And so we put randomness into routing updates in the internet to stop them synchronizing. We put randomness into the back-off algorithms when you try and use the net so you don't all try and retry a busy net at the same time and just make it busier and so on. So that's fairly standard stuff. We have a set of design principles for doing that. There are other design principles for decentralization where you may want to coordinate things before, in an offline way, before you set things up. But then you want to have decentralized coordination when you run the thing, but you may want to have offline checking after the event as well. So you separate timescales. And in computer science, we're familiar with, when do you do binding between this and that? It's a fairly similar idea. So there are lots of examples where this shows up in the successfully decentralized part of the internet with like the address allocation and the name services. So essentially, we have a centralized allocation of prefixes of addresses. We have a centralized allocation of autonomous system numbers, which are what internet service providers use to identify them to each other. But they then allocate the rest of the namespace, the address space that goes with that. But then, for security reasons, you may not believe something you see from somebody else, so you can go off and look at the central registry to check things if you want to. So there's two different timescales operating there. One for the before and after, and the during one has to run real fast now, because you don't get a lot of instructions at typically today's backbone network speeds or data center speeds are 100 gigabits a second is pretty common around the world nowadays. So this decentralized distributed redistribution of identifiers is important. I should say originally the root of a hierarchy of decentralized allocation was the Internet Assigned Numbers Authority, and this was this guy I mentioned called John Postel, whose Postel Principle is named after. He had a great sense of humor. He allocated numbers for documents as well as for the internet. And we had a discussion in year 2000. The American government said they wanted to put in a facility in all the internet to be able to wiretap every internet router. And in the Internet Standards Body, we wrote a document. I was one of the authors. And we said, no, that's a really bad idea. Because if you have such a thing, a bad person will get hold of it. And they will wiretap everything from all the banks and then all kinds of bad things. And John Postel gave us a number for this document that was advice to the US government. And of course, he had to number it 1984, which was very clever of him. He'd saved that number for a rainy day. I wasn't the next free number. He just happened to have it lying around for a useful reason. So, funny man. Okay, so we have this distributed allocation of addresses, and that works pretty well. We have a distributed allocation of ASs. We do need to check things. There are lots of bad things that have happened accidentally in the internet. A small ISP in the Middle East advertises itself as the best way to get to YouTube for everyone in the world. That wasn't a mistake. What they wanted to do was to temporarily block YouTube because it had some offensive content for their nation, for their culture, and they were completely correct. The problem was their next door internet service provider believed them. And so everyone went, oh, look, there's the best way to YouTube. And nobody could reach YouTube because everything went to them and then got thrown into a black hole. Got fixed, but now what we do is we actually go and check, is this person the authoritative source of such information? But that checking is a sort of configure time and then later on sort of just check, do you really believe this? Not at the time of forwarding every packet. So you just make sure it's a slower time scale. So it's just an example of that separation of concerns and then getting you the scaling of large-scale allocation happening with slow time scales and checking, but fast behavior at short time scales. We also have decoupling of the algorithms you even choose to run. You can run different algorithms in a different part of the net, particularly in routing. If you want to deploy a better routing algorithm than Dijkstra, you deploy a better routing algorithm and your bit of the net runs that better routing algorithm. As long as it gets packets from A to B, that's fine. And then you can also deploy better traffic engineering if you come up with a better scheme. So I've already mentioned namespaces. Originally we had all these number spaces. I used to go around remembering these numbers. I typed these numbers in recently. One of them is the name server of the computer lab in Cambridge, so that happens to be its IP address and IPv4. I cannot possibly give you the IP version 6 address because I can't type 128 bits very successfully without making a mistake most of the time. But we have this domain name system, so we have this nice friendly names. But the names now not only decouple things for allocation, and it's a hierarchy, so you get given a prefix, you get Microsoft.com, you can put other stuff if you want, foobar.baz. whatever. But also, it allows you to give different answers when people map between a name and address. So now suddenly we have another very cool thing. We can run load balancers and rotaries in the domain name system. And this is a different hierarchy from the network address hierarchy. It's not connected with business relationships and topologies. It's connected with organizational structure. I won't talk about certificates because they're horrible and we haven't solved how to do them properly yet. Resource management is another area. Decentralized resource management is a good thing. So we have decentralized resource management. Basically, how does the network operate? The network forwards packets. It's trying to maximize the number of packets it gets around, which will maximize its revenue from getting packets around. The more customers I get that I forward their data for, the more I can charge those customers, and they were happy to pay because they're getting their data forward up to what I forward. The user wants to maximize their utility by getting the most throughput for them, or the lowest latency perhaps, but at least subject to minimum latency modulo the speed of light. They want to get the highest download rate they can possibly get, or upload rate. So distributed solution works great. Frank Kelly in the statistics lab in Cambridge came up with this. Peter Key, who worked on it. A bunch of people implemented it in Berkeley in the 1980s. And we have a distributed solution. A bunch of people at Digital Equipment Corporation also worked on it in parallel, came up with the same distributed solution. That's really cool. So we have a distributed resource allocation scheme. Actually, it can be changed. Recently, I'll just mention a couple of things. We've been modifying it so that you can send your data over multiple paths. We'll see why that matters in a second, but imagine you have a smartphone that's got 3G and Wi-Fi and Bluetooth and Zigbee or whatever if you're managing your home devices. Why not use all of them at the same time? Why are you restricted to using one radio at the same time? You'll get all kinds of nice properties from that. That would be good. So matching between the user requirement for maximum throughput and the network requirement for sharing out capacity to maximize revenue, that's done by some feedback, distributed feedback system. That's part of a highly optimized tolerance system. Distributed feedback systems are how ecosystems work. Of course, you can get population fluctuations and so on, so you have to worry a bit about that. But this is distributed optimization, really, really cool. And it's still evolving. And that's really cool because that says we can go on evolving the internet because we've got this distributed solution. Some folks over here modify what they do. Microsoft ship a slightly different version of congestion control scheme in their Windows operating systems. The Linux system has a slightly other different system. We've evolved several times in the last 20 years on this. So it's very, very neat. Okay, so the World Wide Web I've already mentioned is decentralized because URLs are unidirectional. So you can change this site, and you can add links to it. You can add a site and get people to link to it and so on. Of course, you can check for missing links, but that's decoupled in timescale. You can run a search engine that finds things that are bad links and tells people to fix their site. But that's a separate business. So that's a very, very cool thing. There's no centralization in the web. Then it was never part of the notion. Each server owns its data. Of course, you can have copies of a server, you can have replicas, and of course, you can have temporary replicas in caches. That's just fine, as long as you manage the timescales and updating replicas, and that's not so simple, which is kind of interesting. So, okay, let's go back to the cloud, which is what I wanted to say for the sort of main last message of this talk. We made a mistake centralizing everything in the cloud, I believe. I believe this is a mistake. It's been very useful. We've had about 10 years of cloud services, and everyone thinks, maybe... I know. Actually, it's been 6 months since I've been on Facebook. I left Facebook in January. So I don't know what happens on Facebook anymore. I left LinkedIn. I left almost everything, actually. I think the only thing I'm on now, any communication medium, is email. So, but the cloud, centralized. You pile lots of systems in racks, commodity items. They're very cheap. Lots of storage is very cheap. The switches in the data center are not cheap. They're mind-bogglingly expensive, and they use a lot of energy. You could sort of do power saving on all these things, but you don't because most of them are running most of the time, and the backplanes of all these switches don't power down nicely. So actually you burn a load of energy. Power usage efficiency is not that great. So there's a whole green problem with that. But it's centralized. It's subject to attacks. If you If you do the wrong thing to it from an insider attack, which is, according to Ross Sanderson, who's a security guy, a very high fraction of most security problems arise from insiders, you have a problem. The insider could be a security agency, or it could just be a corrupt person, or a crazy person, or a script kiddie. So, why did we lose all those internet principles? Why not decentralize the cloud? Why don't we just go back to this decentralized thing? Why don't you just run your cloud server in your pocket, in your smartphone, right? Why are you running all your stuff over there on somebody else's computer? I've got a device here that's got enough storage for the last 35 years of my email with all attachments. I've got a device at home. I just bought a terabyte disk for $50. That's like 25 times all the documents I've ever written, right? So this is no problem, right? So storage is not a problem. What might be the showstoppers for decentralized? Decentralized cloud would be everyone runs a copy of the social network they want to use, the photo sharing system they want to use, the email system they want to use. They just run their own one, and it has their stuff, and it communicates directly to all the people who are also running their own one. There is no central server. You just directly talk to everyone over the network. That's what the internet does. What are the showstoppers? It's not processing, it's not storage. What it used to be, and we did some work actually with people here, it used to be the uplink speed. The link from you to the rest of the world would be a bottleneck. So if everyone wants to get at my Facebook, which I hope they don't, because it's not there anymore, but when they did, then serving all the 1,500 friends I might have might be a bit tricky once upon a time. But in most of the developed world, the uplink speeds are just getting crazy. 4G, wireless, Wi-Fi, hotspots, ADSL2 or fiber to the home, we're looking at, people increasingly hitting 50 megabit a second. Some of the fiber to the home services lower that a bit, so your uplink speed is only 5 megabits a second. That's actually, if you do the numbers, that's enough. So I did some work with people looking at fully decentralized games. Instead of using a game server, an Xbox 360, whatever you happen to use, you actually decentralize the game completely and play directly to all the other players. You need the inbound bandwidth for all the updates from all the other people. That wasn't the problem. It's the uplink speed from you to all the other people. What's the crossover point? It's around 11 megabits a second, old version of Wi-Fi, 10 megabits a second. That'll do. So there is no real showstopper except this bottom line here, which is the asymmetry of the internet. The internet service providers have been stuck with a very old addressing scheme which doesn't have enough addresses, so they give them out as you need them and take them away again. So you're not reachable all the time. That's not a function of the capacity, it's just a function of a stupid bit of stuff, which we have a fix for, which is being deployed, IP version 6, which cannot possibly run out of, you've got enough bits to address every atom in the known universe and spare. So that's going to be fine, he said. People have said that in the past. Okay, what about a couple of other things I might say? What about, and I kind of did a forward reference here, what about the sort of reliability, availability? Not just can I be reached, but when I'm reached, am I there? Is the stuff working? How often are your links down? Because the network provider has broken a link just by local maintenance. Well, I actually share links with 4 neighbors, my house. We have an agreement where all the routers talk to each other, the home routers, Wi-Fi, just chat to each other. So chances of them being down if we're all on the same provider are quite high. But we're not. We're on 3 different providers. So I have never seen that go down since we set that up about 8 years ago. We've had, but that's without even considering we all have smartphones. So we have 3G and 4G as well. So we haven't even configured that in yet. We haven't needed to. So that gives you 2 kinds of availability. One is you've got failover. The other is you've got diversity, which gives you load balancing for free. There are very cool random load balancing algorithms. Valiant load balancing will be your friend here. So actually it's a win-win-win scenario. So no servers. Everyone's running their own server, if you like. There's no centralized servers, no passwords to worry about. But, of course, you want to encrypt all your data, don't you? Because somebody still might try to hack into your site. So you encrypt all your stuff in storage. You might want to encrypt it even while you're processing it. There's a great research area. If anyone here can solve how to do homomorphic encryption at speed, you will get massive prizes from people, or garbled circuits at speed. There's a bunch of very cool research there. But even before that, you can reduce the attack surface on your system by only decrypting the minimum necessary data while you process it. You don't need to decrypt a photo. If somebody wants to look at a photo you posted on your Facebook, on your server, you send it to them encrypted, and they decrypt it on their device because you've said, here's the key you can use offline in some other key distribution magic. So that would be just fine. So in your storage, in your transmission, they're processing. It's only the last second they do anything, and they do it in the privacy of their own system. So this is doable. We could do this. And we've got some work in the computer lab on a very cool way of avoiding worrying about how you think about all the different keys and passwords you need, but I don't have time to talk about that. But if you're interested in that kind of thing, there's a system called Pico, which uses multiple devices and biometrics and multi-factor authentication. It's very, very sweet. So, and you can then do key recovery for that if you lose all the devices. There's ways of doing that. So why would people buy this? People always say to me, you've done this mad thing, what's the business case? Well, there isn't a business case for this. There is no money to be made doing this, right? Because it's going to be free, but people might like it because it gives them privacy, it gives them provenance and audit trail of who went and looked at stuff, because they see the outbound logs from their server. It's not in Google land or Facebook land or Bing land or Azure land or whatever. You get rid of the requirement to make money for the data center. There's no advertising, there's no analytics, which saves lots of energy, which means you've got much more green networking because you don't have all these big engines running MapReduce or whatever it happens to be. Unfortunately, the bottom line here is quite entertaining. So I'm actually funded, I'm Truth in Advertising, by Microsoft to do research in next generation cloud. And the bottom line here is that if we do this, there is no next generation cloud business. There's no money in it, right? On the other hand, there might be money in new apps. And those apps might be able to do cool new things we haven't thought of. And so, we might move on to the next level of creativity rather than this sort of rather naive model of things. So I'm out of time, so I should wrap up here. And apologies for going slightly long and not leaving much time for questions. Summary is the vision of the network, the once and future internet, the once vision was we had all these decentralized mechanisms. We had a whole family of different tools for doing decentralization of lots of different ways of building the network. And we've lost track of that vision. We've lost track of it, and it's led to some quite bad situations. And it could lead to worse situations as we put more and more of our critical infrastructure, more and more critical information into these systems. This could be quite bad. So we could go back and revisit this whole decentralization, and we then have to face a number of challenges dealing with consistency between replicas that other people have. If you update stuff, there's a challenge. It's an interesting one. Most of the time, people don't update photos themselves. They add new ones. So it's actually not much of a challenge most of the time. And if you're interested in that whole area, sort of eventual consistency is a lovely buzz phrase, which even what it means is not crisply clear yet. And I would claim that there isn't a business case for this, but there is a national cybersecurity case and a citizen's case for it as well. It's something we should kind of think maybe we want it. You might kind of say, yes, but my grandfather can't work out how to use a Mac, let alone this. Won't have to, right? You don't have to. It's all going to be gesture-based. It'll all be done for you. That's not a problem. That's a usability question, which are very cool people dealing with. But where that data resides, maybe it will be somewhere where they can at least have some notional trust about it's not being fiddled with by some random person they've never heard of. Okay, and it may be much more resilient to bad attacks and so on. It will give them lower latency access. There's a long list of plus points, which I think I've hopefully made plain. Okay, so I'll stop there, and we have a few minutes for questions.
Thank you very much.
Hi, I have a question regarding the collective intelligence. How does it fit into your decentralized architecture? Thank you.
So what exactly do you want to know about it?
You said that you were mentioning about collective intelligence, yes. And how would this fit? So if each of the people have their, I don't know, preferences or stuff like that, how would this fit in this new decentralized?
Okay, I don't think that decentralization or centralization is germane to that question. So whether it's centralized or decentralized, I need to be able to communicate with a set of people. But a decentralized system, the internet is decentralized, and I can communicate from this device to the device in my pocket direct over the local Wi-Fi or Bluetooth, or via a server in the US if I want. The distributed intelligence question was a high-level thing I just wanted to point out as a sort of other topic, which I think is a very nice one, which is the original goal of the internet was to provide something. Originally, the RAND report that was written that led to the internet was how do we support groups doing activities so that the group can work more effectively. So the example I point out where people have tried to do this in the civilian world is actually the Pirate Party in Germany, where they got a few people elected in their government, and they didn't have any policies except on copyright. And so they crowdsourced policy. And they built a system, but they also had to build a system that was very clever because they had to deal with trolls and people misbehaving. So that was a social tool, not a technological tool at the low level. And they did a lot of clever work that is quite like the Wikipedia work, which prevents edit wars. There's a bunch of tricks, but they're almost like they're support for human protocol to reduce the damage made by misbehaviors of people. And there may be a link between that and low-level misbehavior of users attacking things on the internet as well, but I haven't made that link. But I think the liquid democracy, if you look at it, several people have tried to implement this. There's some group in Italy that's trying to implement it in a local government where you get direct engagement of people and you try to engage people continuously rather than just having a referendum every now and then about things, and people are empowered by that. But you have tools that prevent this race to the bottom, which is the usual problem. As you add people, you get this race to bad behavior. Sort of everyone's trying to, the few people that are bad sort of take over the conversation. So that's what I was referring to there. Decentralizing all the servers, I don't think has a plus or minus point on that particular way of doing things, although I could imagine you could think of some connection that might be interesting to look at.
So I just wanted to ask you, as a young researcher in networks, we've seen a lot of interesting strategies, let's say, for instance, related to data center transfer protocols, and then let's say content-centric networking, and things like you mentioned MPTCP. So sometimes when we're working on these new ideas, one thing that comes to mind is that many of these things never actually then sort of come onto the internet. So it's sort of like a how can you say it, a demotivator. So could you sort of perhaps guide someone like me that what should we do, or how should we think about approaching these problems?
That's a great question as well. The internet is very, very, very big, so having an impact with a really good idea is really hard, and it's almost a matter of accidental luck whether few people actually get something to work, get it out there. I think one of the best things you can do in my experience the last 20 years has been working with big industry research labs who have links to operational people. So working with Microsoft Research is a good example. There are lots of such organizations. And then you would, if the work you do looks like it's really going to work, they will ship it. So one of the things we did with MPTCP, so I'm in the project at the multi-pod TCP, there's a bit of a detail here. We managed to persuade some people at Apple to use it. So now if you use Siri on the Apple service, it actually uses MPTCP. And they shipped it, and it was like, oh wow, that's like, okay, we're done now. Our job is done. We don't have to do anything else. I mean, it'd be nice if Microsoft did, and I know they've got ideas in that space as well. But so working with somebody is, I think, the best way to have, because you're trying to add things to a massive operational infrastructure now, and you have to be very patient. So the timescales for something to happen. One of my students and I worked on a thing called SIP, which is how voice over the internet works, signaling. It's kind of being used now. We did the work 20 years ago. So you have to be very patient to actually see something, make it out there. So during a PhD or a postdoc project, it's unlikely, it's not impossible, particularly if you work with a big research lab, and then you can get that leverage. And plus also they'll have filters for choosing what they work on, where they think that that's something that there won't be too many barriers. Also, of course, in the operational internet, there are barriers which are not their business or non-technical barriers. So sometimes you can have something that's definitely, I mean, you mentioned content-centric networking, could be the best way to do things. You just can't get it shipped because other people have some vested interest in something else that's not as good, sadly. I don't think one should not do work because of that, but if you want to have a big impact in the world in how many people use your bit of code, that's kind of tricky, and what I encourage is think about how you collaborate with industry labs and people that have those pathways to get stuff out there.
Another question?
Hi, thanks a lot for that great presentation. I just wanted to point something out. You described the first hackers as bad boys, but don't you think that by revealing bugs in the system, it actually helped make the internet more robust? And second, if you go to books like Hacker's Ethic by Pekka Himanen, you can see that these weren't really necessarily bad guys. And actually, you just then gave an example about the Pirate Party. And if you see what the Pirate Party did in Iceland, how they reformed the constitution, most of the ethics come from the hacker culture.
Yeah, I'm right. The problem with the word hacker, of course, it has two different derivations, but in fact, they're not separate, they overlap. And a lot of people who worked on the early internet sat in that overlap area and still do. And a lot of innovation happens in the open source community. There are people that are motivated to go faster TCP or go faster web servers or go faster cloud servers. And there are two guys we're working with right now sat in a desert in North Africa for the last 6 months writing a better implementation of transport layer security in a language called OCaml. And we're now cooperating with Microsoft, who are doing another implementation so that we can run model checkers on the two. But these two guys are hackers. But what are they doing? They're trying to fix something that's got a whole bunch of weaknesses, fundamentally a better way, and so Microsoft. And so we've got this sort of corporate research group, but also corporate development of something, and then there's this hacker community, both well motivated. So I totally take your point, and I think it's well made, and I think it's sort of, I think you can learn a lot by going in those communities, and even in the really sort of strange parts of the, it's a lot of fun as well. Yeah, if you go see people setting, we run just a bit of advertising. We run a conference called ExtremeCon, where we take people to a random part of the world where they have to get there themselves and build a network. And we started out in Lapland, up in the Arctic Circle, and we did one in Iceland, and somebody had to be helicoptered out because they broke their leg and we were in the middle of nowhere, and we did one up in base camp in Everest. And you just go up with a bunch of gear and everyone arrives and tries to build networks. And we do with some of the Burning Man people. And it's the reason for that is you want to build networks out in places where they don't have any money to pay for a network. And then you do it. Unfortunately, the funny thing here was that Everest Base Camp had the best 3G and Wi-Fi coverage. So we showed up. It was completely pointless going there. So, but all the other places was fun. So, but yeah, it's a well-made point, sort of social point that these communities are not, there's not the bad people and the good people. That's the wrong model.
Question here?
So one of the important reasons why we centralize things today, both computing and networking infrastructure, is the efficiency, like the need for consolidation. So where does your proposal stand with respect to efficiency, energy efficiency, for example?
Well, I'm not sure. There's a scale-out efficiency of a data center in the sense of the economy of scale of buying a lot of stuff. But all the edges are now wasting resources because all the edge devices people already have high-res displays. They already have a lot of storage. They've already got enough memory to run a serious operating system. They have a shed load of storage to cache video content and so on. So actually, all this centralized system gains an efficiency of scale. To some extent, it's actually not that great. And the edge systems actually already have the resources. You did not need that central system. So I'm not disputing if you compared 100 small data centers with one massive one, the bigger data center is better. But if you fully decentralize to the edge, then I think I would claim we use less resources overall. And we've done the numbers for this. There are certain breakpoints in the overall resources, so it's not always true. So it's
not about just possessing the resources; it's also about using them. So the
sure.
operational costs.
Well, so. Right, so most home systems are far more energy efficient and do power saving modes much better than centralized systems. So as long as I'm not serving my Facebook pictures to everyone 24/7, my system will be down most of the time and they'll be on wake up on packet mode or whatever. Whereas a central system will have to have some resources up the whole time because there'll always be some users tickling it with some traffic. So I would claim, we can have an offline discussion about the detail, but it is a breakpoint thing. There are places where the balance is in favor of what you're saying. What I'm saying is we're moving to a point in terms of edge resources where I think the balance is in favor of the fully decentralized approach. Of course, you can have a hybrid. That's fine, And if everyone's using edge resources, but occasionally a central resource is useful, it can have, better power saving modes than it currently runs and have a lot less systems running. That might be fine. I have a sort of view of the world where you put a data center in every car, and if every car is electric and is all plugged into a network and a charger, you've got power for your data center in every car. You're never more than 100 meters from a car, and you can time shift the use of the network and the data center and charging the battery in the car. So you've got a whole world there. We've got lots of medium-sized data centers around the world. And that's efficient because you need to time shift energy use for electricity anyway when we move to that world. So that's another discussion we could have. But I think you're right at a certain point in history, and I think we could move away from that again back to the mine model. But
Last question here.
You actually tied right into it. It seems that we're balancing on a spectrum between two extremes, that of total decentralization, every user their own server, and that of total centralization, to have a single giant mainframe Facebook out there. Well, one happy medium solution might be to have geo-replicated data centers that provide availability in different regions, safety for when your home gets demolished by a flood, and plenty of other analytics bonuses too. Shouldn't we go more for that solution than for total decentralization, to each user their own?
Yeah, no, it's a fair question. We're just taking a position for the purpose of seeing how far we can go with a full decentralized solution. Part of it is we do need to provide archiving and backup of replication. But the way we do replication is we stripe the data using some network coding technique, resilient coding technique, and actually clever rateless codes, which we didn't make up, but lots of other people have, over all the other edge systems from time to time. And that gives all those systems plausible deniability. None of them has all the data to reconstruct our data if our home is flooded, but a small K out of N of them can recover our data. You could move that to a number of small data centers as well, and just have them being a backup archiving service. If you had homomorphic encryption, because also you could pay for that by then doing some analytics, maybe, or differential privacy preserving mechanisms for data mining what you've got without giving away individual information. So I think there are intermediate solutions. So I totally buy that.
Okay, thank you very much, John. We wrap up here.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.